Hey kids, welcome to our last topic of the year. Isn't it crazy? And it is going to take us 2 videos to get through, but still, it's the last one of the freaking year. Oh my goodness, I had to take a sip of my coffee. All right, polar curves. Day 1. So, objectives. Find the slope of a polar curve. Now remember, we are talking about being on the XY plane, just like we were in parametrics. We're on the XY plane, so let's suppose that I want to find the slope there. I want to find the slope of the curve. That's dy dx. But when I have r, a polar curve, in terms of theta, r prime is just dr d theta, right? So to get dy dx, notice there's no r in here. I just have dy d theta and dx d theta. That's dependent upon you knowing that, hello, y in polars is equal to r sine theta, which just comes, this all comes from like your unit circle, right? And x is equal to r cosine theta, right? Notice that y and x are in terms of r and theta, but it is a product. So to find the slope of a polar curve, I need to make a ratio of dy d theta, which means I have to take the derivative of a product, dx d theta, which means I have to take the derivative of a product. So let's do that. Notice they are asking me for an expression, not a number. Unless I'm multiple choice, I'm not going to clean this up much either. If they just ask me for an expression, they're going to get what they get. So here's my polar curve R. It doesn't matter if you recognize, you don't need to recognize what that is, okay, on the graph. Nobody's asking you to graph it. You just need to recognize that this is a polar curve, R in terms of theta. You do need to remember that y is r times sine theta, so there's my r. X is equal to r cosine theta, so here's my r times cosine theta. Dy d theta then is the product rule. You must do the product rule with both of these, but the product rule never changes. First function times the derivative of the second plus the second function times the derivative of the first. Dx d theta, product rule. Product rule never changes. First function times the derivative of the second plus the second function times the derivative of the first. So dy dx is a ratio of those two things. And again, I'm not going to distribute, combine, not unless I'm matching multiple choice. But I do want you to look at some pattern things here. Notice that in both the numerator and denominator, I see r. Do you see that? But you have a negative right there, right? Look at what else I have. Go up, back up to the original, where you see r, and tell me what r prime is with respect to theta. Do you see that? That's in both the numerator and the denominator. Both r and r prime are there, and both are just multiplied by sines and cosines, or a negative sign. So some people like to just memorize a formula, which is fine, right? Because I could have, finding dy d theta, I didn't have to use this particular r. I could have used the product rule with just r in general. The derivative of y, which is r sine theta with respect to theta, and the derivative of x, oh, I dropped an r, x with respect to theta, and made a ratio of them. And again, the d thetas cancel out, but I have to do the product rule, do a little rearranging of terms, and look what you have. Just so they don't have to lead with the negative, right? They put r prime first. In the numerator, r prime is multiplied by sine. In the denominator, r prime is multiplied by cosine. Then they also have r, right? In the numerator, r is multiplied by cosine. In the denominator, r is multiplied by negative sine. So if I had, instead of using doing the product rule for each one, what if I just memorized this formula? I would have had to found r prime, but I would have done that and put it in the numerator and denominator. I would have multiplied the numerator by sine, the denominator by cosine. Then I would have put r, multiplied the numerator by cosine, and the denominator by negative, positive cosine, negative sine. And if you notice, those two expressions are the same. Okay, so it doesn't matter to me how you do it. What I do want to know, make sure that when you are asked for an expression, give them an expression. Now I'm going to move to what if they ask you for the slope at a point. So if they ask you for a slope at a point and you have a calculator in your hands, don't you dare do any of that work. But if they ask you for an expression, whether you have a calculator or not, you got to do this work. So what if I said I want the slope of the curve at, put it here, dy dx at the point 2 comma pi, which is r comma theta. You have to put theta in for all of your, you have to put pi in for all of your thetas. Fortunately, pi with sines and cosines isn't so bad, right? Notice what happens. You get 2 minus 3 times sine of pi, which is 0, times cosine of pi, which is negative 1, plus sine of pi times, who cares? Sine of pi is 0. Notice down here, 2 minus 3 sine of pi makes this little piece 0, but you're multiplying by negative 0. So this whole piece of the denominator goes away. Cosine of pi is negative 1. Negative 3 times cosine of pi is negative 3 times negative 1, which is 3. So I have 2 times negative 1, and I have 3 times negative 1. So I get positive 2/3. That is the slope at a point. If they ask you for an expression, you gotta find it. If they ask you, but you just have to do this work. If they ask you for the slope of a point and you don't have your calculator, you have to plug in your theta into your expression and evaluate. However, if they ask you for the slope at a point and you have a calculator in your hands, so please pause. If you don't have your calculator, go get it. You know how to put it in polar mode, right? You just go to mode and choose polar. Polar coordinates, you might not know how to get to polar coordinates. Polar coordinates, hit second format, which is above the zoom. Hit second format and arrow over that top choice there, arrow over to polar, GC. I wonder what GC said. Graphing coordinates? I don't know. So do both of those things. 1, 2. Now hit your Y equals screen. And when you hit Y equals, you're going to notice that you don't see Y equals, do you? You see R. So put R into into R1. 2 minus 3 sine theta and hit zoom trig. Make sure you're in radians. Now you won't see my picture. You hit zoom trig and you will get a little bit, you'll get the bottom of this limestone cut off. Right? Just go manipulate your window and move your Y's if you want to see the whole thing. But zoom trig is always a good place to start. So let's suppose they wanted the equation of the tangent line at 2 comma pi. I have my calculator in my hand. Hit trace. And notice if you have the polar coordinates turned on, R is 2 and theta is 0. You don't want theta to be 0. You want theta to be pi. You can't input the 2. Unlike rectangular coordinates, you input the x and get the y. For polars, you input the theta and it will give you r. So you hit trace and then second pi, and you will see, and you'll see the point that we care about. Right, so here's my calculator picture. So I hit trace and then I hit pi. This is pi. And it gave me the cursor point right there. Now, that's swell, but they wanted the equation of the tangent. The equation of the tangent means I have to write y equals slope parentheses x minus x coordinate plus y coordinate. We already found the slope to be positive 2/3, right? But let's pretend that we didn't do that by hand and we're going to use the calculator. Hit second trace. What do you see? Choice 2. Hit choice 2 and then hit pi, and it will give you the slope at pi. We did this by hand. We found dy dx was equal to 2/3 because we got the formula and we put pi in. But if you have a calculator and you are asked for the slope at a point, do not do all this work. You just get in polar mode, turn on your polar coordinates, hit second trace, choice 2, dy dx, hit pi, and you'll get your 2/3. Now, you didn't get the tangent line, but you got this, right? Do you see that that's 2/3? But you can't put 2 comma pi there, right? The slope of this line, dy dx, the rate of change of y is 2 compared to the rate of change, 2 units compared to 3 units, 2/3. And this line certainly looks like it has a slope of 2/3. But to write the equation of the tangent line, I need the x and y coordinates. This is where you have to remember that x is equal to r cosine theta, and y is equal to r sine theta. So who cares what r is? Sine of pi is 0. So my y coordinate is 0. I hope that makes sense to you. Can you see that? So I'm going to put a 0 there. But my r is 2 minus 3 sine theta, which for me is pi, times cosine of pi. This goes away because sine of pi is 0, so I have 2 times -1, which is -2. So -2 goes there, and that is the equation, I have parentheses there, of the tangent line, dy dx. Y is equal to 2/3 x plus 2. Cool? So again, when you have a calculator and you are asked for the slope at a point or the slope of the tangent line, or write the equation of a tangent line, use your calculator, polar mode, polar coordinates, dy dx, second trace choice 2, angle, which is pi, and it gives you your slope. Pop your slope into there and then use your formula to get r and, to get your x and y. Now, how I got, if you want to know how I got the graph, the line on to make my calculator, you hit second program. Choice 5 is tangent, and you tell it the angle that you want the tangent drawn at. Now, you can always also change your coordinates back to rectangular and trace over that point and get -2, 0 as well. Not so bad. Okay. Now, in your book, part of your homework is going to ask you questions like this, or to find the slope at a point, and it gives you like 5 points. I can't make you, but I suggest that the first one they give you, do by hand. Practice finding the expression and then plugging in. But then the rest of them, just use your calculator. So I use my calculator, so do this with me. Enter 0, right? Do second calc, choice 2, dy dx, theta equals 0. And you're going to get 0, aren't you? No, you're not. You're going to get -2/3. Sorry, I was ahead of myself. -2/3. Do you see it up here? What if I asked you to write the equation of that tangent line? I hope you're not too surprised by finding out that's going to be +2, 0. How about at -1 pi over 2? Do dy dx at pi over 2, and look at what I've drawn up there. Hopefully you're not surprised. This has a slope of 0. What's the equation of the tangent line, do you think? Y equals r cosine, right? R sine theta. Right? Can you see what that's going to be in rectangular form? How about this one? On your calculator? That slope is also 0, but it's not the same tangent line, is it? Right, does that make sense? Okay, slope obviously of 0, right? You're putting a 0 there, and then you're finding the x and y coordinate using our formula. Psych, I can see I don't really need my x coordinate, right? Because my slope is 0. So again, this is what I suggest for your homework. Number 42, I suggest doing the first one by finding the derivative expression, then using your calculator to find all of the actual values at a point. All right. So here is a different polar equation. Suppose the position of a particle is described by a polar equation. Again, you don't need to know what that looks like. If they want a graph, they'll give you one. You will not have to graph these yourself. You'll either have a calculator or they'll give you a picture, or they'll do both. But look at this question. When theta is pi over 3, is the particle moving towards or away from the origin? What? What? All right. Change your r, right, in y equals, but it'll be what? Put this into your calculator and get this graph. When you do, hit trace. So you're hitting 2 sine 2 theta. Do you remember what that is? What that's called? This one's an easy, right? It's not like limazon or cardioid, right? This is a rose. 4-petal rose. So hit trace pi over 3, and you're about right here. Right? There's my point when theta is pi over 3. And they want to know, is the particle moving? Moving. That's not dy dx. That's the rate of change of the radius with respect to the angle, because that's how I'm plotting. Radius, angle, radius, angle. So what is dr d theta? Well, you've got r. What's dr d theta? Don't forget the chain rule, please. R prime is 2 cosine 2 theta times 2. So sometimes this prime notation can be confusing. Might be helpful to remind yourself that's the rate of change of the radius with respect to theta. So if you understand how you're, right, and again, you don't need to understand a whole bunch, but when you graph, right, here's the radius to that point. There's the radius after, right, when I rotate pi over 3 radians with this length of a radius. So what is dr d theta at pi over 3? Thank you, Speed Trig, because I don't have a calculator with this. Cosine of pi over 3 is 1/2. 2 pi over 3 is in quadrant 2, so cosine is negative. What does it mean when your derivative is negative? Think about on your xy plane. What did you do with when your derivative is negative? What does that mean? Your function in not polars, in function mode. What does it mean? You're going down, right? Now I need to transform that thinking into polars. So you're doing the rate of change of radius. The rate of change of radius with respect to your angle is negative. So what do you think that means your radius is doing? Means your radius is getting shorter, is decreasing. If your radius is decreasing, where is this point going? If this point was going this way, wouldn't the radius be longer? Right? As pi starts from 0, right? Because you are going in this direction, right? Counterclockwise. So where is the point going? It is going towards the origin. Right? That's kind of cool. But you do have to realize what it means to plot a point in polar. So what if I gave you a different point? What if I said, how about I said when theta is pi over 8? What's dr d theta? The rate of change with, right? is 4 cosine 2 theta. So that's 4 cosine pi over 4. Positive. Positive. Now hit trace again and hit pi over 8. Look at where you are. You're about right here. When theta is pi over 8, is the particle that's moving along this path moving towards or away from the origin? At this time, the rate of change of the radius with respect to the angle is positive. So the radius from the pole, the radius is getting larger. So therefore, right, you are moving further away from the pole. So you can't make this, oh, always positive, right? You have to think about the graph. Where is it? And again, you will always, BC is not testing to see if you can plot points, if you can name the graph. They're seeing if you can interpret what's going on with a polar equation relative to being on the xy plane when I want the equation of a tangent, or how is my particle moving along. So what if I asked you, look at this multiple choice question. Nope, this is not relative. This is a whole separate example. It's not talking about the graph that we just did. Interpret the meaning of any dr d theta when dr d theta is negative. Look at the first choice. The slope of the tangent is negative. How many of you are going to choose that? Please don't. Concave down has something to do with second derivative, certainly not the first. But look at C. The distance between the curve and the origin is decreasing because my rate of change of the radius, right? So is that towards or away? It just depends upon where I am. But wherever I am on my polar curve, if the rate of change of the radius is negative with respect to theta is negative, I'm going to be, my distance, my radius is going to be getting shorter, right? So the distance between the curve and the origin is decreasing. Kind of a cool thought process. All right, last thing for this one, the length of a polar curve. Length of a curve, what is that, right? Length of a curve on the xy plane was the integral of Pythagoras. And remember, it was 1 squared plus dy dx squared. And then remember with parametrics on the xy plane, but parametrized, the length of the curve was still the integral of Pythagoras, still a sum, still derivatives, but dy dt, dx doesn't matter, dx dt, dy dt, you're adding and squaring, so who cares, right? And this was from time equals a to time equals b. So now I want the length of the curve, but with polars. So with polars, right, in parametrics, I still had x's and y's. With polars, I am dealing with coordinates, though, that are r comma theta. So check out what that looks like, right? Isn't that kind of cool? It's still the integral. It's still Pythagoras. You still have a derivative squared, but the derivative is dr d theta, not dy dx, and the radius, instead of 1 squared, it's r squared. And then notice it is with respect to theta. So you're taking dr d theta. You have an expression for, right? You have r in terms of theta, which means your limits of integration are theta values, right? From 0 to pi over 2, from negative 2 pi to 2 pi, from 0 to pi, right? So what if I asked you to find the length of this cardioid? You don't have to know it's called a cardioid, but it shouldn't surprise you with cosine is oriented xy. Cosine goes with x, so look how this is kind of like oriented in the x direction. There's a negative, so it's kind of longer in the x direction. This one and this one are the same, which is why you have this cardioid hitting the pole. Don't care. Just care about the length of that curve. You do need to know that it takes, right, going from the period of cosine is 0 to 2 pi, right, is a length of 2 pi. So that's where theta equals 0 and theta equals 2 pi comes from. So notice there is r, and what is this? R prime. dr d theta is equal to 0 minus negative sine theta, which is sine theta. Everybody's in terms of theta. Oops, I left off my d theta. My limits of integration in terms of theta, I'm just plugging this into my calculator. By the by, I don't need to be in polar mode to do this. I'm going to lie to my calculator, right? I can just be in regular function mode, right? And I can have, right, and just use x's. But when you set it up, make sure you use your thetas. Excuse me. And this is a very nice number, 8, because it's a pretty graph. All right, that's it for this, and we'll do some quick review. Again, we'll practice going back and forth for rectangulars and polars in our live session, and we'll do some more examples, and then we'll move on to polar area. See you in our next live session.